TLC stands for thin layer chromatography. It's an experiment that's often used in winemaking to determine the presence or absence of certain acids. In a commercial winery, you're more likely to see paper chromatography being used rather than the thin layer technique being shown here. This is due mainly to reasons of cost efficiency. The chromatographic material that we use is a layer of aluminium or polycarbonate bonded with a thin layer of white silica. The silica is a thin layer of extremely fine sand, and adsorbed to this fine sand is a layer of water molecules. In effect, the surface that our acids come into contact with is actually a layer of water molecules, and since the water molecules are very polar, polar materials tend to be retained towards the baseline. This will become more clear when you see the finished chromatogram at the end of the experiment. For this experiment you need two of these sheets. This one I've labelled sheet number 1, and it's used to run our acid standards. You must remember to only use lead pencils when marking these sheets, and to do so very carefully with no pressure applied. You can see that I've marked a line indicated by the red arrow, which is to be the starting point for our acids. The first spot is for tartaric acid, now indicated by the red arrow and marked with a T. The second spot is for malic acid, marked with an M. The third spot is for lactic acid, marked with an L. The fourth spot is for succinic acid, marked with an S. And the last spot is marked all, and this is where all four of the acid standards are applied on top of one another. Here you can see our four acid standard solutions, being tartaric, malic, lactic and succinic acids. In each sample tube is a capillary tube, and this is what's used to transfer the standard solution of the acid onto the TLC plate. It's vitally important that these capillary tubes are not mixed up between samples, otherwise experiments can easily be ruined. To apply a sample, take the capillary tube and touch the silica surface very gently but rapidly. This will ensure that your spots aren't too large. To speed the drying process up, you can use a heat gun, as you can see here. Next, apply a second spot, dry and repeat the process so that you build up 4 cumulative spots for each sample. When you've completed sheet 1 in this way, you can move on to sheet number 2, which has the acid standards in addition to your wine sample. Sheet 2 is prepared in exactly the same way as sheet 1, using consecutive heating and spotting to build up the sample concentrations. Whilst the sheets can be prepared at the bench, the next part of the experiment has to be performed in the fume hood. The solvent used for this experiment is particularly toxic, and it needs to be kept in the fume hood at all times. Using a pair of tweezers, place each of the sheets into a solvent jar. Ensure that there's at least half a centimetre of solvent in the bottom of the jar, but make sure that there's not so much that it dissolves the spots off that you've just spent ages putting on. It's also a good idea to ensure that the sheets are sitting as vertically as possible and not touching one another. You will be able to see the solvent migrating up the TLC plate, shown here by the lower grey section. The acids migrate at different speeds depending upon their polarities. When the solvent front gets close to the top of the plate, remove it and mark the solvent front with a pencil line and then dry it in the fume hood. Once the plate is dry, it needs to be dipped in the indicator solution. Again, this has to be kept in the fume hood at all times because the indicator solution is also toxic. Using tweezers, dip the plate into the indicator solution very rapidly, allowing any excess to drip back in. You can then place it aside on a piece of tissue paper and replace the top on the indicator solution. The drying process can be assisted by using a heat gun. After this time, if the spots are difficult to see, you can try re-dipping it in the indicator solution and drying once again. These plates are quite good examples of what you can expect. Since we've used an acid-base indicator to colour the plates, acids here show up as yellow spots. Note that the spots have moved to different positions on the plates, and as I said before, this is dependent upon their polarity with respect to the solvent and the surface of water molecules. Note also that spots don't necessarily move the same amount on two different sheets, as you can see by the uppermost spots at the right of each sheet in this image. This doesn't mean that the experiment has failed, but what it does highlight is the importance of having that one spot with all samples at the one position. In this way, an internal reference is always present and problems like this can be overcome. The RF value or retention factor is calculated by dividing the distance that the spot has moved over the distance that the solvent front has moved. Here you can see the tartaric acid spot, the malic acid spot, the lactic acid spot, which is typically very faint, and then the succinic acid spot, which is usually quite intense. In the last position we have all standards of tartaric, malic, lactic and succinic acids. Moving to sheet number 2, we once again have our 4 wine acid standards of tartaric acid, malic acid, the faint lactic acid spot and the succinic acid spot. The positions of the standard acid spots tells us where to look for these acids in our own wine sample. In the more concentrated wine spot you can easily see tartaric and malic acids, and there's maybe a faint trace of succinic acid there as well. Since in this wine there is a malic acid spot with no lactic acid spot, it's quite obvious that it has not undergone malolactic fermentation.